Welcome to Section 1, Video 2 on SVG Basics. In the previous video, we covered an overview of the course. In this video, we'll be discussing the building blocks of D3, scalar vector graphics. Scalar vector graphics are what compose the simple shapes, paths, polygons, and arcs out of which most common visualizations in the D3 library are made. Whereas traditional image files like JPEGs, PNGs, or GIFs reduce file size by eliminating details and colors not necessary for a crisp picture as you zoom in, SVGs actually tell the browser how to draw a particular shape, so SVGs can be redrawn at any level of detail. SVGs have been around a long time, but have made a resurgence with HTML5 standards and high-definition screens. In this video, we're going to lay the groundwork for making more polished bar charts like the one on the screen, working through how to include tooltips, automatically generate axes and labels, and add on hover effects. There are a variety of beautiful D3 visualizations that can also be checked out on D3.js.org if you're looking for inspiration, ideas for your next project, or instruction on advanced methods. But first, let's tackle some basics. Let's jump into the editor and start by creating a rectangle, or rect as they're called in D3. For the sake of ease, just copy the following tags into a basic HTML body. Let's start with the SVG tags. They create a block level element in the DOM that's essentially a canvas onto which other shapes can later be appended. Note that we've given our SVG a height of 200 and a width of 300. This is the space into which our rect will fit. Inside of our SVG, note that we've given our rect an x value of 50 and y value of 100. This will position our rectangle within the SVG. Save your file so we can take a look at the result. Once you've opened your file in the browser, use your dev tools or inspect element to check out the blue rect on the screen. You should see the SVG functioning as a container for your rect, extending 50 pixels to the left as well as 100 pixels above the top of your blue bar. Both positions placed in our x and y values we gave our rect element. If you're wondering how a x value of 50 and y value of 100 ended up placing the rect on the bottom left of the SVG, well, besides a little bit of padding left, it's because x and y coordinates start 0, 0 in the upper left corner of the SVG. So our x component pushes the bar to the right 50 pixels, while our y attribute takes up 100 pixels of the SVG's height, of which the remaining 100 is accounted for in the rect. This aligns the rect with the bottom of the SVG. The fact that we have to manually compute what height and y value combinations will place the rect on the bottom of the SVG, as well as how our width and x values place rects side by side to build a bar chart, can get a bit problematic, particularly when you start dealing with more or shifting data. This is where D3 comes in our next video, and streamlines the process. But for this lesson, let's just build a chart the old-fashioned way, so as to see what components go into its making. Let's jump back into the editor and check out the next snippet of code. First, comment out the initial block, and then continue by entering the following example. Notice that we've specified a width of 75 for all of our rects. Multiplied by 5, that accounts for 375 of the 425 px SVG width. We also placed our first rect with an x-coordinate of 50, giving ourselves a little bit of space and taking up the entirety of the SVG. The height of every bar has also been subtracted from the height of the total SVG to give us our y values, effectively pushing the rects to the bottom of the SVG. Let's check out what this code looks like in the browser. While the method works, it's really pretty hard to maintain or adjust if you want to add or subtract data points. And we've just arbitrarily selected a width and height for our SVG that have very little to do with the data being presented. With that in mind, let's move into the next video to see how D3 can streamline this process and help us out with simple yet easier to maintain and responsive visualizations. See you then! Welcome to Section 1, Video 3, making a D3 bar chart. So far we've learned about the basics of SVG. We will work through making a bar chart with D3 in this video. As we saw in last video, it can be burdensome to maintain an SVG-based bar chart that's hard-coded in HTML. So let's work through some D3 basics to create the same bar chart, but one that's dynamic and easy to maintain. After some of the following sections on labels and axes, we'll have a modular, reusable D3 bar chart. Let's start with walking through the simple boilerplate we'll be using for a number of sections. For this boilerplate to work, you'll need to download the latest version of D3, place it in a subdirectory of your project directory, or simply use the cdn, which at the time of this course's recording is here on line 5. Continuing on to our bar chart, we'll want to start with a few basic variables, including one for the height, the width, padding, and our dataset. The values in our dataset variable are the ones we'll eventually want correlated with the shapes in our SVG, in this case some bars for our bar chart. The W and H variables will just be used later for ease of calculating measurements in relation to the height or width of the SVG. But first, similarly to our hard-coded bar chart, we've got to set up our SVG. We're going to be calling methods from the D3 object for every step of our visualization, so let's store this section in a variable that we can chain methods to give our code slightly more clarity. What we've done here is access the D3 object, and then the select and append methods. D3 allows methods to be chained with dot notation. Like dot notation in vanilla JavaScript, a dot after the object allows you to access that method or attribute of an object. In this example, the D3 object is used to utilize the select and append methods. Method chains in an end and semicolon, so the previous declaration isn't finished. It continues with an attribute method, which sets the attributes of height and width for our SVG. Attribute methods can be used once you've selected the element to which they apply, and in many circumstances are utilized to pass data and index values of pertinent datasets to a function that returns values. Note that you can use a number instead of the W or the H variables, but as they'll be repeated throughout the visualization, we've just included them as variables. Now that the SVG is set to be appended to the body, it's time to pull in some elements that will become the bars of our bar chart. With our dataset already declared above, we simply have to attach our data points to individual rects, one rect per data point. Data binding, or the process of establishing the dataset for your visualization and then attaching it to visual elements, can seem a little counterintuitive at first, but is a crucial part of almost every type of D3 visualization. It starts with the data method, into which, for our purposes here, the name of an array into which we've stored the points we would like to plot is passed. Then the inner method is called. This iterates through the elements in our dataset, and for each passes a placeholder, nothing visual is yet been established, to the append method, which attaches a type of visualization for each placeholder. Now keep in mind that these visualization types still won't be visible as they don't have attributes, but the process at least binds data to primitive D3 types that could later be manipulated into the look you would like. Notice that there hasn't been a semicolon yet, and the method chaining continues. As with the hard-coded copy of our bar chart, we need to give individual recs their attributes such as x, y, width, height, and fill, so we add the following code. The collection of values in this attribute method is called every time a portion of the dataset is passed through the data method and entered. We start with an x value that adjusts depending on how many points we have in our set. I returns the index value of the data point being placed into the bar chart and multiplies it times the equation that divides the width of the SVG by the number of objects in the dataset, creating equally wide bars for each, no matter how many bars in the bar chart. The Y method streamlines having to subtract the difference between the bar's height and the height of the SVG, so that bars are aligned on the bottom of the container. Because the values of the dataset are rather small, when translated literally into pixel terms, display for the data values, we've multiplied the values by 4 in this section, as well as in the height attribute section below. In the width section, we've subtracted a 2-pixel padding from the width of the entire SVG divided by the number of data points in our dataset. This provides a bit of space between each bar for added clarity. Finally, the fill attribute spices up the otherwise black bars by making them teal or red according to a condition. Forgot padding. Now, if you will save your 1.3 source code, we should be able to move to the browser, and voila, there is your first D3 bar chart. If you would like to see the dynamic nature of the bar chart, try adding in several more values to the dataset. Due to our width value that calculates according to the length of our dataset, you should see individual bars shrinking. Theoretically, this chart could adjust to include more data points until the bar charts are only slightly larger than their combined padding space. This could be remedied by making the padding dynamic, perhaps a percentage of the total space, or a function returning 0 if the bar gets too slim. This won't apply in many cases, however. Note that the actual shapes that have been appended into the SVG and DOM can be manipulated through CSS. They're the exact same recs that we had hard-coded into our HTML version of the bar chart. With this in mind, let's head back over to the editor and change the color of the recs on a hover events. As simple as that, and we have our first bit of interactivity. Now that we made our first D3 visualization, let's move on to the next video about making a line chart with D3. Welcome to Section 1, Video 4, Making a D3 Line Chart. In the last video, we walked through creating a bar chart in D3. In this video, we'll get our first taste of some of the more powerful features in D3, like drawing paths, a method that will be built upon later when dealing with geographic projections, as well as working through a basic line chart. Let's get started with our line chart by establishing the width and height variables for the SVG, as well as establishing our data set. For this project, we're going to keep our data in an array of hashes, each index value of the array containing a month and a corresponding win percentage. Next, much like we'll do in all of our projects, we need to establish the SVG. Because we haven't differentiated which portion of our data set will correspond with X values and which with Y values, we'll need to use the D3 line method to establish these facts. Our variable line1 will take the data set that is passed to it, iterate through month keys, and return the value of these keys multiplied by 33. We chose 33 because we're only going to be using 12 months, and the total width of the SVG is 400, which is roughly 12 by 33. These values, or 33, 66, 99, and so on, will be the X values of our line. They'll be paired with our Y value, a value found from iterating through the dataset passed to the method and checking the value accessed through the win percentage key. We'll multiply these values by 3 to move them more into the middle of our SVG. And then we'll subtract from the height, so that the higher our win percentage, the higher the line will climb. Otherwise, it would be inverted. Together, these will be linked through the interpolate method, which can take a number of instructions on how to string together points into a line, but of which we've chosen a simple linear. This prepares the data to be appended to a path and make a line. A final step is to append a path and to give it attributes. Let's walk through the following code. First, we've appended a path to our SVG, which chains methods all the way back to the D3 object. Then we've given our path attributes, such as D, to which we've passed our win percentage by month dataset, through our line1 call to the D3 line method. We've given it a stroke of blue, a stroke width of 2, and no fill. Note that as with many of the other simple D3 visualizations, first we select a body and append an SVG, and then we select the SVG and append the other primitive visualization type that we're trying to make a chart with. Now that we've added one line to our line chart, let's save our document and open it in the browser. If you'll inspect the element or open your developer tools, note that D3 has taken pixel values as computed from our win percentage and month data types and converted them into path elements inside of the SVG. Adding a second line is as simple as appending a second part to the SVG. I've added a dataset with a format matching the first. We'll then need to make a second call to the D3 line method and pass in our dataset too. And finally, append a second line. The same as the last time, save this time with a stroke of red. Let's save our document and see what it looks like now. Notice that both of our datasets are plotted onto the same SVGs. Now that we've worked through a simple line chart, let's move on to the next video, where we will learn how to plot circles as a function of data into a scatter plot. Welcome to the 5th video of the first section on basic non-interactive reusable charts. In the previous video, we covered making single and double line charts, as well as the basics of plotting a path in D3. In this video, we will work through making a scatter plot using D3. We'll explore how to plot circles that can form a scatter plot, look at another simple visualization method, and prepare for the next section on scales, axes, and labels. For a scatter plot, we can start out with the same basic components as our line chart. After all, a scatter plot is basically just the points of a line chart without a connecting line. We'll want a few more data points and slightly greater variability to really showcase what scatter plots are good for, highlighting outliers and clumps and potentially disorganized data. So let's start with our height, width, and data set. While we're using the same hash format, save with 24 months this time, note that we could use the index value of an array we're cycling through instead of the month value key. After all, it does just iterate up 1 every single time. Yet scatterplots will usually be used to portray data with components that are well represented along 2 axes, time and percent in this case. Next, as we've been doing in all of our visualizations, we'll declare the SVG and place it in a variable. With nearly identical syntax for creating the recs for our bar chart, let's bind our data to circles and append our circles to our SVG. We'll then need to give our circle attributes. The attributes that are necessary for points in a scatter plot include CX, CY, and radius, as well as a fill value if you would like for your circles to be any color other than black. As you start making D3 visualization, it's useful to start naming the segments of your code in predictable ways. Note how our first circle maker appends our circle placeholders to the SVG, while circle attributes gives attributes to those circles. As simple as that, let's save our visualization and check it out in the browser. While this particular visualization may not show a particularly striking trend in our sample scatter plot, it is important to constantly grow the array of relatively simple visualization techniques at your disposal. This is important for responsive data visualizations, as you will often employ different forms of a visualization at different screen sizes or on different media types. As an example, let's say the larger values are really those that the viewer in your visualization will be interested in. Just assuming this is the case, it might be a good opportunity to utilize a size-based reflection of the data, at least on some screen sizes. While viewers should be able to hover over plots with their mouse and read the tooltip on full screen devices, they may have trouble clicking on the proper values to see more info on smaller size screen. So a visualization style enlarging the clickable space would be optimal. We accomplish this enlargement through the function returning values for our radius, where we've taken the square root of our wind percentage and exported it in pixel format. Now that we've worked through a simple scatter plot, it's time to move on to our next section, in which we'll learn to add scales, axes, and labels to our previous visualizations. This will lead to modular, interactive, and dynamic D3 charts. See you then! Welcome to Building Responsive Data Visualizations with D3 by Pact Publishing. My name is Meryl Cook. I've been a data journalist for several years, working on both static and interactive data visualizations, ranging from infographics to interactive maps to scrolling sites that tell a story with data. As someone who regularly assembles and publishes visual content, I've come to respect the immense importance of responsive design in data viz. And while there are a number of good D3 courses and tutorials online, a complaint I regularly see is that there aren't many resources that integrate D3 know-how into a responsive mindset. That's the idea for this course. Not one that simply focuses on making D3 visualizations, but rather on how D3 visualizations work in real-world contexts, where content management systems, a panoply of screen sizes, and regularly shifting datasets can get between your visualization and your site's viewers. I'm hoping my content experience will help to steer the course towards answering many of the most pertinent questions about not only making D3 visualizations, but deploying them on live and changing sites. Over the last few months, I've also been involved in the process of ramping up a new project called OnlineCourseReport.com, a site that seeks to provide resources and a searchable database for potential online learners. I'm especially grateful for the opportunity to dive into the creation of an online course at this time, and to see what really makes an online course work. But enough about me. Let's talk about the course. There are three central components that I hope to achieve in this course. First, seeing as it is a course on D3, is that students should be able to create a number of basic, reusable D3 visualization types. While that's as far as most D3 courses go, we're going to take it a step farther. The second component includes a basic knowledge of responsive design, as well as Twitter Bootstrap. Through a few examples, we'll proceed through many courses on responsive design cover. The third, and perhaps most important feature of the course, revolves around applying our knowledge of responsive design to our D3 visualization. What do you need to render at what screen size? Where should you place data visualizations on a page? Does functionality change for different screen sizes? And then how do you implement those choices? We'll start with a section on basic non-interactive reusable charts. This will help ground us in the syntax and workflow essential for all D3 visualizations. In the second section, we'll upgrade our initial visualizations by utilizing scales, axes, tooltips, and labels, elements essential for polished-looking charts. In the third section, we'll move on to the basics of responsive design and look at what mobile-first strategy entails, as well as making previous examples responsive. The fourth section will enable us to massively increase the range of possible visualizations we can make by tackling external data sources. We'll work with CSV, JSON, and Geo Data to eventually render a map. Section 5 throws in some interactivity into the mix and lays the groundwork for more responsive visualizations through introducing the notion of rendering and re-rendering visualizations depending on browser event. We'll build off of sections 4 and 5 and 6 and 7, where we'll construct a choropleth map of the US and then make it responsive, learning how to utilize a number of quality tools in responsive design. Before we continue, I should note that for viewers to get the most possible out of the following videos, they should at very least understand the syntax and have some practical knowledge of HTML, CSS, JavaScript, and jQuery. If you don't feel up to snuff on one of those topics, there are a number of great tutorials online that can give you enough of an understanding to proceed with this course. I feel that this course is ideal for designers with some front-end knowledge who are looking to expand their toolset, for front-end developers who are looking to get into data visualization, back-end developers who are looking to bridge the gap between databases and visualization, or anyone involved with online content with some front-end knowledge, such as editors, content producers, personal bloggers, or marketers. If you're interested in learning to build a wide variety of D3 charts, layout types, and maps in the context of learning responsive design, this is just the course for you. See you in the next video.
Hi, welcome to Section 2, titled Building Blocks 2, Adding Scales, Axes, and Labels. In the last section, we covered some basics of non-interactive charts, including bar charts and line charts. In this video, we'll be adding simple text labels to our visualization. We'll also cover choosing what data makes a good label and when labels should be used. Let's pull up the code from our previous scatterplot example. The simplest form of labeling involves taking values in your dataset and appending them to your SVG as text elements. Let's start by binding data to our soon-to-be text elements. Note the similar order to appending elements to the SVG. Making a selection, specifying the location of our data, entering the data, and appending it as an element. Also notice that we've chained onto the SVG variable that we previously used. This is so we'll have the location that each data point is plotted as a reference point from which we can adjust in choosing where to append our text. Now that we have some placeholder elements assigned to data, it's time to give our text attributes. We start by chaining to our previous text maker variable, giving elements the same x and y values as the circles previously appended to our scatterplot. We then use the .text method to specify where to find the values that we would like appended. Necessary attributes for our text element include font family, font size, and a fill color. Note that you can also format the text as a function of your actual data. An example could be taking the number of data points in a given data set and returning a text size based on how many points there are. When building an interactivity, it's important to note that the text elements will take up space that often overlaps the elements they're labeling. Best to include a z-index value for both the element and its label. Note that we've included a z-index value of 0.2 for our circles and 0.3 for our text, so that the appended labels will show above the element they're labeling. Also of note is the fact that you can append text elements selectively to pull out particular numbers. This is what we do with our text attributes.text method, where we check to see if our data.win percentage values are above 60 before seeing if we'll return each specific win percentage number. In the event that they are, they're returned as labels, which will be appended through our .text method. Let's save our work and see what it looks like in the browser. Note how the last .text method alteration leaves text elements only on the elements meeting our conditions that win percentage must be greater than 60%. Now that we understand how to add plain text elements to visualizations, we should move on to the next video on creating tooltips for our visualization. See you there! Welcome to Section 2, Video 2, Creating Tooltips for Your Visualization. In the previous video, we learned how to add simple labels to your visualization. In this video, we'll learn how to create tooltips. First, we'll be creating divs with opacity values of 0, adding a mouseover event handler to your visualization, and showing the previously invisible divs when the mouseover event is triggered. Let's continue by building tooltips into our scatterplot. The basic components at work here include a div containing a label whose position attributes are altered based on where the user's mouse is when an event listener is triggered, when the mouse hovers over the circle. Our tooltip div will have a bit more styling than we want to include through D3 syntax. So let's add some styles, either in the head or in a separate style sheet. Note that this is a pretty basic div element with 100px width, 28px height, and absolute positioning so that it will overlay any other visualization elements from the location at which the mouse triggers the event handler. Relative positioning would let the normal page flow, including the SVG, push the tooltips to the side so that it might not even be visible to users. Let's continue by appending a div element to the body. and specifying a class of tooltip. Note that we've given the div an opacity of 0 so that it won't show up upon the initial loading of the page. We'll want to specify the transition away from 0 opacity in the onMouseOver event handler that we're about to set up. Let's head over to the circle attributes variable to chain our onMouseOver and onMouseOut event handler. Check out the D3 documentation for all of the types of the .on method, but just know they can include events like click, mouseover, or submit. Their general format is .on, parentheses, type of event, listener, and capture. Note that D3 also has a touch method for screen touches. We'll need to add the following code on lines 85 through 98 to the end of our attribute method chain in our circle attributes variable. Stepping through the code, first we're listening for a mouseover event, and then we're calling the following function. Our function transitions the CSS of our div over 200 milliseconds to an opacity value of 0.9. It also adds HTML to our div element, including a header of win percentage and the value of win percentage from our dataset. We've then styled the position of our div with the D3 event.page listener. This listener returns the location of the cursor on the page as an XY value whenever the function is triggered, which enables us to pass the same value as the location of our div, save for the fact that we've altered the Y value by 28, so as to bump our newly formed tooltip slightly above the cursor. The second .on method listens for a mouse out event, which is when the cursor leaves the circle, and slowly fades the div back to an opacity of 0 over half of a second, or 500 milliseconds. Let's save our work so far and open it in the browser. Note that whenever your cursor initially goes over one of the scatterplot circles, a tooltip is appended until you move your cursor away. If you open up your DevTools or Inspect Element and locate the div element below, you should see the incremental adjustment of the div's opacity left and top values. Now that we've added some quality-looking tooltips to our scatterplot, let's move on to the next video on utilizing D3 scales. See you there! Welcome to Section 2, Video 3, Utilizing D3 Scales. In the previous video, we learned how to add tooltips to our previous scatterplot example. In this video, we'll be learning how to utilize D3 scales. We'll start by covering some concepts crucial to scales. We'll then initialize some scales and apply them to our previous scatterplot example, showing how scales can make D3 code simpler and more powerful. Mike Bostic, the creator of D3, has about the most accurate definition of scales on his Definition of D3 Scales page. He notes, scales are functions that map from an input domain to an output range. If you haven't used them, you may have to come up with a mnemonic device to remember that. But basically, scales are a good way of converting inputs into values scaled to your particular visualization. You define the parameters of scales, can use as many as you wish, and can call on scales through the .scale method. Note that scales are simply a mathematical relationship, and not necessarily in the final visual output. But they are used to create their components that are in the final visual output, the axes. Scales are crucial for responsive data visualization, as without them, you're often using direct interpolations of data as pixel measurements, which, particularly with dynamic data, can quickly run over the edges of your screen sizes. Let's head back to the editor to start seeing how scales can help our scatterplot visualization. Let's start with the domain. This is the spread of potential values in your dataset. Using the win percentage data of our previous scatterplot, the domain would be 3 to 110. The output range is up to us to choose, with the smallest number being the value you would like the smallest data point to correspond with. Often range numbers will be actual pixel measurements you want to give as attributes to appended elements. The maximum range value will be the largest amount you want as an attribute for an element, say, for a bar chart, slightly short of the pixel height of your SVG. Note that we've initialized our scale with the following code, d3.scale.linear, and stored it in a variable called scale. D3 and scale simply initialize our code, while linear is the type of scale that we'll be using. We then set the input domain to the lowest and highest numbers in our dataset, and our output range to 10, just off the bottom of the SVG, to 350, the height of our SVG. To see if our scale is set up properly, open up your scatterplot visualization and head to your DevTools or Inspect Element. Start by entering scale with different numbers between parentheses to see your scales at work. Note that it takes numbers between 3 and 110 and plots them onto a scale between 10 and 350. Therefore, 109 becomes close to 350, while 4 returns close to 10. This is all fine and good for small and unchanging data sets, but what about if we have tons of data points, or they're changing over time? Here's where the D3min and D3max methods come in handy. They both work similarly and take parameters that start with the source of the data you want evaluated, and then usually provide a function telling the method how to access particular values it's supposed to be looking through. To use the D3min and max methods on our win percentage entries in our dataset, we can type the following into our DevTools console. Notice how the D3max method, when applied to our win percentage by month dataset, and requested to return our win percentage values, responds with 110. The highest number in our dataset that we had previously located. Min and max can become great helps if you're dealing with datasets with many more points. Let's head back to our editor to implement min and max. Here we've set up our Y scale, X scale, and R scale. Remember how at the start of the lesson I mentioned that you can set up as many scales as you would like, each taking their own parameters. While our previous variable scale showed us the basics of how scales work, it's technically not needed from here on out. Note that we've provided a domain for our Y values, ranging from 0, the lowest potential value, to the maximum of our win percentage by month D.win percentage values. By supplying the height of our SVG as the lowest value in our range, we've alleviated the need to subtract all height and Y values from the height of the SVG. Essentially, the higher the domain input to our Y scale, the closer to the height of the SVG, lowering it on the final visualization, and vice versa. By subtracting a few pixels from the maximum range of our X scale, we made sure that some of the circles on the far right of our SVG won't fall off the edge. For our R scale, we simply scaled the radius of individual dots between 2 and 10, depending on their win percentage values. Now that we have dynamic scales in place, we can begin to apply them as our CX and CY values with our scatterplot circles. Previously had arbitrarily positioned the circles for the SVG, we can insert our X scale and Y scale. Note that it's simple as returning the values that we get when we pass the locations of our data through our scale methods. Now that our scales are being used to parse our data into visualization-specific values, let's check out what our visualization looks like in the browser. Notice how our scales have converted our data into a format that takes up the entire space evenly. Because we used the max method, our X, Y, and R scales, we're also in luck as far as adding new data points. We can add as many as we would like, and as long as they aren't below 0, our visualization should adjust accordingly. Having learned how scales can optimize our D3 code and make it dynamic, let's move on to the next video on adding axes. See you then! Welcome to Section 2 of Video 4, Adding Axes. In the last video, we looked at how to add scales to our scatterplot. We're going to build off that lesson in this video, so as to render our scales as visual components of our visualization. We'll explore the range of data that can be included on axes and make some quality of life improvements to our code. As we're going to be adding our axes to the left and bottom sides of the scatterplot, and our current scale extends all the way to the bottom and left of our SVG, we should start by clearing some room for the axes. Start by subtracting 20 from the Y and X scales, like I've done on lines 72 and 75. The syntax for adding an axis is pretty straightforward. In general, first you're initializing the axis through the d3.svg.axis method and telling it what scale it should operate on. Then you're actually calling the axis below to render it onto the SVG. Another optional method to include is .orient. For the x-axis, the default value is bottom in quotations, but both bottom and top may be chosen from. It should be noted that top or bottom orient values do not move the line on which the axis ticks are placed, but rather the direction that axis ticks point away from the line. For the y-axis, left and right values may be chosen from. Because the default orient value for the x-axis is bottom, and for the y-axis is right, we've simply altered our y-axis orient value to the left, so that our ticks can face outwards on whatever axis they're attached to. By giving the axes a class of axis, it will be easier for us to style all of the components of each axis later on. The selectable elements of an axis include path, line, and text, so those will be the particular elements to address when we're styling in our CSS. Let's save our work and check in on how it's looking in the browser. Looks like we're missing our y-axis, and our x-axis is on the top instead of the bottom. We'll have to use transform translate to get them both into the proper positions. The transform attribute takes the translate parameter. which in turn takes an X and a Y value that will correlate with where you're moving a given element that's selected on the SVG. Note that we don't want to shift our X-axis any to the right or the left, so I've provided an X coordinate of 0. Rather, we're trying to shift our X-axis down the entire height, and thus the height. I've also included a variable towards the top called axis padding that's set to 20px to move the axis up a little bit and keep it on the SVG. Save your work and let's see how our transform translate call came through. Our x-axis is in the right location, but it's still a little bit ugly. Let's head over to the CSS to see how we can make our axis a little bit better looking. If we wanted to change the font family or size, we would do that through the .axis text selector. And what we have added, the fill value set to none, takes away most of the bulk that was in the previous axis line. If you haven't seen it before, shape rendering is a CSS property that applies to SVGs and tells the browser what trade-offs to make in rendering shapes. Options include auto, optimized speed, crisp edges, and geometric precision. Auto balances attributes, with slight favor given to geometric precision. Crisp edges emphasizes the contrast between SVG elements. One final note on our x-axis that we won't currently add, but I'll just talk you through, is that the .tick method may also be added to D3.svg axis chain. This suggests the number of tick marks that the axis should have. D3, however, reserves the right to override this request if the numbers for each given tick denomination don't come out clean. So we've got our x-axis set up. Let's move on to our y-axis. Save for a different transform value when appending the axis, and an orient value of left, everything is identical to how we established the x-axis. For the transform translate call of the y-axis, we've established a value of 30px for our x and 0 for our y values, because we don't want it to shift up or down, simply right so that it's inside of the SVG. Because we've applied the same class to our y-axis, the same styles should apply as well. Let's save our work and see what it looks like in the browser. It looks like our y-axis is pushed slightly too far into the right, as it's encroaching upon one of the circles, and the y-axis 0 value is slightly cut off by the x-axis. To give ourselves a little more room, we'll want to adjust the x scale. Let's head back over to the editor to make these changes. Let's add 10 to the x scale range to give ourselves a little bit more breathing room. After saving, we can jump back into the browser and see our balanced axes at work. While it's nice to have good-looking labels, that might be a little too many ticks to be practical. Let's return to what we were saying about the .tick method and add the following snippet to both of our x and y-axis calls. Looking back in the browser, you can see that D3 has taken slight liberties, applying 7 ticks to our y-axis and 6 to the x-axis. It looks like D3 thought that this was as close to our requested 5 ticks, where each denomination could actually present pretty numbers. With our axes completed and looking nice, and a look at the number of components needed to make quality dynamic visualizations, it's time that we move on to the next section. See you in section 3, Responsive Visual Strategies. Welcome to the third section of Building Responsive Data Visualizations with D3, Responsive Visualization Strategies. In the last section, we covered tooltips, scales, and axes. In video 3.1 on defining responsive and mobile-first design, we'll be looking at why mobile-first has become important. We'll then move on to creating a grid-based site layout that helps our mockup fluidly transition. Since 2007, laptop and desktop penetration have remained relatively unchanged. The biggest shift has been in mobile user growth, with mobile users now outnumbering desktop and laptop users worldwide. The growth of mobile for all types of media consumption, as well as the proliferation of tons of different screen sizes and resolutions, has led to the growth of responsive and mobile-first design. The term responsive design was coined by Ethan Marcotte in a 2010 article on Alistapart.com, predictably titled Responsive Web Design. In the article, responsive design is likened to the emerging discipline of responsive architecture, in which physical spaces respond to the people who pass through them. As far as the definition of responsive design, you can see Ethan's comments on the screen. Ethan focuses on 3 core techniques for keeping your projects responsive. 1, a fluid foundation. 2, flexible content. This is where D3 comes in. And 3, media queries. A fluid foundation involves moving away from pixel measurements and towards proportions onto which a page can be divided. This is where the mobile-first aspect comes into play. If you can establish a fluid foundation that gives crucial info and functionality to users on the smallest devices, scaling up should be a piece of cake. starting mobile first is also practical, as there's more of a standard smallest screen size developers deal with than a largest screen size. So if we can make a site or visualization work in the context of a 300 pixel wide screen, we can then use a proportion-based styling and some media queries to make similar designs work on larger screen. If nothing else, you'll have more room with which to get your design across to visitors. Flexible content is where D3 and SVGs become involved. If we build off of a flexible base, we can create visualizations with SVGs that redraw themselves and that work in a variety of sizes, something we'll see later in this section. A good example of how seamlessly D3 can redraw SVGs can be seen on this example from brendonsodal.com. With a self-updating donut chart, it is also responsive. Note how not even the animations are disturbed by changing screen sizes. Enough talking now. Let's move into the editor and get some hands-on experience with a small grid and making it flexible. As you may know, an iPhone screen is 320 pixels wide, so let's start by making a common column-based layout with a width of 300. Inside of your basic boilerplate, paste the following code. This is a common layout that we're going to make into a grid. One row with a span 4 column, a second row with a span 1 and a span 3 column, a third row with 2 span 2 columns, and a final row with 4 span 1 columns. With a little bit of CSS, we can make our grid visible. Enter the following into the style tag of your header. Note that we've set our body to 300 pixel width to approximate the width of an iPhone screen, and we've centered it with its margin. We then divided the 300 pixels width into denomination of fourths. Well, almost, once we've accounted for the 10 pixel margin right that's attached to all of the elements. So we subtracted 10 px from the 300 px container width for every element in a given row, and then divided by 1, 2, 3, or 4, as noted in 65, 140, 2010, and 290. We've also given each span its own color so that we can see what's going on in the browser. Let's open up the browser now to check on the result. It looks about how you would expect a 300 pixel grid to look like. However, our design is still fixed width, and so not really supportive of fluid transitions, different sizes of screens. Let's continue on to alter our column layout and base it upon proportions so that it adjusts depending on the screen size. For this, we'll need to use a commonly used formula in responsive design. Target width divided by context. This should give us a decimal that we can then convert into a percent. Let's jump back into the editor to check it out. Here we've taken the previous pixel widths of our span and margin right property and divided them by the context area, or 300 px. But we want fluid transitions, not simply a 300 px body width for every screen size. So we should change the body element to a width of 90%, which with the margin centering the body will leave about 5% free space on either side of the screen. If you don't follow how we got our proportion-based measurements for our margin right and width for our span, do the math detailed in the comments to the right of every span. Walking through one more time, we essentially took the pixel value that was the previous width and divided it by the total width of the context, 300 px, after subtracting the number of margin rights that have been applied to that row. Let's jump into the browser to see our new slightly more flexible layout. When you resize your browser, it's starting to look a little bit more like what people normally expect when they say a page is responsive. But it's missing one component, the content. Plus, you would probably never want a series of 110 pixel height divs for a full-size screen. So that's where we're going to head in the next video, where we'll look at media queries and how they can help us to provide additive CSS for a number of different screen sizes in which our content doesn't quite fit our site layout neatly. But before we go, let's review what we covered in this section, including the basics of responsive and mobile-first design, making grid site layouts, and using percentage and proportion-based designs. The next video is on using media queries and addressing breakpoints. See you then! Welcome to section 3.2, using media queries and addressing breakpoints. In the last video, we looked at defining responsive and mobile-first design. In this video, we'll look at building a responsive small screen site and then adapting that site to tablet and full-size screens, alleviating breakpoints as we go. If your site is centered around presenting content instead of functionality, and we're assuming this is the case due to the data visualization context we're working with in this course, we want to make sure your site is responsive in a way that makes important content easy to see and interact with at any screen size. To this purpose, we're going to work on a very basic mock-up of a traditional news engine style page on which you might find a data visualization. Let's start small, first imagining a mobile version of the site. I've already created a simple version of what our small screen news site can look like, so jump into your editor and grab the video's example code. This time I went ahead and used external style sheets, so open up main.css as well. A basic rundown of the code is that we have a black header set to 100% width, 5% max height, with the position of relative. This will keep it at the top of the page even if we continue adding header elements. Currently inside of the header, there's a logo class and a menu class, both of which have 49% width value, the remaining 2% of which will be accounted for with padding and margin. They've both been displayed in line block, and the menu class has been floated right. So they both should fit inside of the header element. Below that we have a nav element, which takes up 50% of the page width and is centered with its margin. Our header image div has a width of 100, with the actual image inside of the header image limited to a max width of 100. This will keep it matching the size of the container div until it reaches its original size. Below that, the width of our small screen social icons set to 64%. Through adding up the cumulative widths of each individual icon and dividing them by our context of 300 pixels. 48px is optimal size here. As noted by Apple, 44 by 44 pixels is the smallest space most people can easily click in a touchscreen environment. You've probably encountered pages that made design errors in this vein, as you would try to click on elements and instead click beside. Also note that the width of our article class is 90%, and it's centered with a margin of auto. There are also some readability features here, such as an 120% font size and 1.2 line height. These are great for a mobile-sized environment, but probably not how you would like to organize a larger page. Without further ado, let's see what our code looks like in the browser. With the screen size down to around 300 pixels wide, everything looks decent, albeit simple, and seems to give us the general functionalities of mobile-optimized pages. Users can peruse the article, there's social sharing icons, and some reduced menu capacities. And meanwhile, images take up the entire width of the screen. Make sure your dev tools or console are open to get a read on the width of the window and start making the window larger. Everything adjusts smoothly into extra space. This is particularly easy at this size, as most of the inner elements simply split the space of container elements with percentages, while most of the outer elements are centered in the event that there's any extra room. Looks like everything is fine until you get to about 480px. You'll notice that at greater widths, the header image stops enlarging, and thus also doesn't stay centered on the page. That's because this is the header image's original size, and it won't expand anymore. While we were able to shrink it, not overextend the page at smaller sizes by placing it at a max width of 100%, the buck stops here. There are some things we could do to make the layout expand in a bit more balanced way, however. We're close to 480 pixel width, which is the starting size of many larger phone displays. And we just need to keep the display balanced for a few hundred more pixels before we're in tablet land that could add some more functionality to take up space. Let's head back over to our style sheet to see what we can do about this. First, we'll wrap our existing CSS in a media query which is applied at a minimum width of 280px. So it basically extends to all screen sizes, unless we make further clarifications down the road. Next, let's start with the clarifications we want to make. We'll start by specifying our next breakpoint at a min width of 480px. By adjusting the header image holder div, which is the div directly surrounding our header image, we can keep our header image sizing up to its original size until the next breakpoint. We've done this by dividing the max width of our header image by the context of a 780px breakpoint, which gives us 60.15%. We've also centered it, so that as it enlarges, it'll take up the center of the screen, slowly growing larger from 480px minimum width to the next breakpoint. We also made our small screen social icons slightly wider. This will keep them from rendering horizontally and break them down onto each of their own rows. As their own rows, they'll be pushed to the right of the page, thus taking up a little bit of the extra space through these slightly larger screen sizes. Let's save our current work and jump back into the browser. Note that once we get to 480, our social sharing icons jump to the right, and our header image begins to resize again on its own, from the center of the screen this time. Everything looks balanced through the larger phone pixel widths, but we're moving into territories where users would begin to expect a bit more functionality. If we move over to the next version of the source code, 3.2.2, you'll see the adjustments made for a 700px site layout and larger. There are a lot of small changes to our code between the two versions that you can look at on your own, but they're really just centered around a few points. At a min width of 780px, we've included a second column to the main body of content. It includes an About Us section, a Recent Post section, and a Social Actions section. These have all been included under a Span1 class, with a width of about 24%, or roughly a fourth of the layout with a bit of padding subtracted. We've shifted the social sharing buttons below the section by giving them a similar width, 25%, and floating them right. The article class has also been shifted slightly and given a span 3 class in the HTML, with an inline block position and a float to the left. This will allow our text to float to the left with our new elements floating to the right. One final note is because our screen size isn't huge yet we've incorporated a number of new elements, we've shifted our header image holder up to the top in the left so as to make slightly more room. While there are tons of articles, some based on data and others are sharing preferences about the best media query width values, it should really be dictated by your own content. Notice how our next min width value of 975px is slightly lower than many suggested widths of 980 for a media query. This was to fix a small glitch where text was creeping up into our images at larger screen sizes. The simple message here is when the site layout can't handle your content without glitching, that should be where you insert new style rules. If you'll look at the minimum width rules for 980 and 1200px, they're basically extensions of the same arrangement. The main differences being the content div takes up 80% of the max width for the 975 min width media query and 60% for the 1200px. We've simply reduced the width percentage and kept it center, an easy way to keep things tidy and remain cognizant of the fact that we won't need to use the entire page at larger screen sizes. Let's look in the browser and check out what our responsive site looks like. Of course, it could look better, but it's just a quick sketch of how to use media queries to better present your content on diverse screen sizes. One final note, there are two angles through which you can make a site responsive. The angle we previously pursued starts by working on a mobile-sized screen and scaling up with the use of min-width queries. This method starts with a style sheet at the smallest screen size denominated, and whenever a new min-width is specified and other media queries are reached, stacks the new styles on top. The second angle is sometimes better if you're starting with a fully constructed full-size site. This method involves scaling the site down with max-width queries, in which new styles are applied starting at specified maximum widths. With our site relatively responsive and our breakpoints addressed, let's move forward to the next section. As you move forward, remember the importance of regularly checking for breakpoints, as well as the fact that there aren't specific points at which you always need media queries. It's really quite site-specific when layouts break down. The next video is on choosing a visualization style based on media type. See you there.
Welcome to Section 3, Video 3, Choosing a Visualization Style Based on Media Type. In the previous video, we learned how to locate breakpoints and address media queries. In this video, we'll work through smart visualization strategies for small, medium, and full-size screen or media types, as well as some current trends in data visualization. Let's start with small device screens. The most prevalent form of data visualization in small screens is the dashboard. Perhaps it's your banking app, or some form of gamification in a course you're taking. But it's generally not the pure web page-centric data visualization that we're talking about. Just Google image search dashboard data visualization mobile, and a ton of mobile-centered designs pop up. As far as the visualization we've been dealing with, line and bar charts are some of the best represented in terms of their ability to be fully responsive and resized to mobile-specific screen size. An example of a line chart that resizes nicely, as most of the charts coming out of NPR's awesome visual teams do, can be seen in this GIF of an NPR story. Notice how the number of ticks respond as the screen size shifts, and how smoothly the line chart is re-rendered at different dimensions. Another option for small size screens is simply to change the format of your data visualization. The following example isn't D3, but shows an interesting data visualization on the migration of notable people throughout their lives. It has been packaged into a nice curated video. In some cases, it's best not to give users data to explore, but rather to completely curate the experience. This might be best when a dataset is overwhelmingly large. Some maps work at smaller screens, but it's best to scale the map to where it takes up more than the entire screen width, such as the following example. Otherwise, the intricacies of clicking between winding map boundaries can often become tough. If you're hoping to show a macro trend with your map, you can make the map extremely small, but that generally gives up the ability to easily interact with the map on small screens. A good example of this working can be seen in small time-lapse maps that show a transition over time but aren't truly interactive. There isn't much to say about medium-sized screens, so that you'll likely want to retool your visualization to make use of one-touch interactivity instead of on-click or hover. Many tablets are large enough to see the entirety of a data visualization, even if they must take up the entire page, where they would fit into a container on larger screen sizes. One example of a nice medium-sized screen visualization can be seen at tylervegan.com, with the recently popular spurious correlations. Part of the genius of these visualizations is their simplicity, and the fact that they can be churned out every few minutes. The same applies to the site layout. which isn't fully responsive, but is just flexible enough to size down the extra space in the margins to center the content on tablet-sized screens. Large screen sizes are where the entire arsenal of D3 can really be shared, particularly in interactive maps and series of visualized elements that fit together in a series. There are countless examples of good full-size screen visualizations, as most D3 visualizations have traditionally been built for viewing in a full-size browser window, with a mouse, for full exploration of datasets. Particularly nice utilization of an entire screen visualization is put on by Enigma Labs' exploration of weather anomaly data in the following example. Using the spread of the page, slightly different denominations of the same data is presented in a number of formats to be explored, from time-lapse map to line to bullet charts. In summation, we've worked through some food for thought for future visualization strategies that can work on small tablet and full-size screens, and even some good visualizations that are simple and aren't built responsively. With no more ado, let's move on to the next video that centers around matching the size of charts with the size of their container. See you then! Welcome to Section 3, Video 4, on matching chart size with container size. In this video, we're going to be looking at how you can use the margin element to scale SVG elements with their containers, enabling D3 visualizations to be redrawn at different screen sizes. We've got a lot to get through, so let's jump into the editor and get started. In course code sample 3.4.1.html, let's start by setting up the container that our D3 SVG will be placed into. Start with the usual boilerplate and a div with the ID chart in the body. We'll style the body with 90% width, and the chart container with 80% of that width down to a screen size of 400px, which will enlarge our chart to take up 100% of the body. Notice we've also colored our chart red so that we could see this transition in action. Save your current code and open it in the browser. Note that we have a flexible div into which we can place our visualization, taking up the entirety of the width of the window at less than 400px, and 80% of the 90% body at every other width. Let's jump into the 3.4.2.html source code to continue. You'll see we built upon our previous code, and then we're going to set up a basic bar chart, but instead of using hard-coded width and height values, we're going to use D3's margin feature that looks at the computed styles of the selected divs and uses them to translate a position for our SVG element. Let's begin by changing the height of our chart element to 100%, and also by removing the background color, as that was just for seeing the basic page layout more clearly. If you look down into the actual code, you may feel like this is quite a bit more code than it's taken to render a simple bar chart in previous sections. But there are really just a few basic actions going on in our new code. After our typical looking bar chart dataset, you'll notice a string of declared variables with titles relating to positioning and sizing. The margin element looks at the container size and creates a margin between that container and the element to which it's applied. We'll be using it to establish our width and height, as you'll notice in the following lines. To start out, we've adjusted the margin to 10px in every direction. The main reason we're using this tool is so that we can establish the width based on the container directly below. Notice we establish our width by specifying the width style element of our selected chart into the parseInt method, which returns an integer value. We then modify the width slightly by subtracting the margins specified above, margin left and margin right. The ratio declared below is how we establish regularity in the ratio between height and width. For some elements like maps, you'll want to be more exact, but in our case we simply need to specify the ratio of our width we want our height to be. 0.3 means roughly that our width will be 3 times the length of our height. Notice we apply the ratio by multiplying it times the width in our height variable. Now that the margin element is computing our height and width based on the size of the container that will hold the SVG, all we have to do is specify width and height like they were static elements. Next, jump down below the resize function. We'll tackle that in a few. And take a look at the expected code. Notice that we establish our scale using our width and height that are passed from the margin element. And then we use those scales to give the recs that we're appending to our SVG our Y value. Note for a bar chart, we don't pass any function of our data for the X value, because we simply want the SVG divided across the X-axis equally for the number of things in our dataset. What we currently gone over, excluding the resize function, would allow our chart to be redrawn at different sizes whenever you refresh the window, but not to dynamically adjust when the screen size changes. To truly be immediately responsive when the browser is resizing, we need to listen for screen resizes. For this, head to the bottom of your document, where we use the D3 select method on the window, and then offer the event handler on resize, and call the function called resize. This means that every time a window event of the type resize is triggered, we'll call our function resize. Moving up in the code of the function, you can see that the resize procedure begins by selecting the SVG element and removing it. There are a number of ways to do a resize similar to this, but for our purposes, we'll just remove the SVG, then redraw it based on the new container width values gathered by the margin element. Notice how we've respecified all of the values we specified after our initial margin call on lines 40 through 44. After this, we'll append our chart again, and the new width and height values will be applied throughout. Every time the window resizes again, the same process will be repeated. Note that there are basically just three parts to our code. A margin that grabs the size of the container element, the portion of the code where we initially draw our bar chart, and then a function that destroys the old chart and re-renders it, this time with new dimension. Let's open up the file in the browser to see if it works. Note that it sizes down and up until it hits 400px, at which it takes up the entirety of the width. The next video is on scaling all elements of a visualization based on container size. See you then! Welcome to Section 3, Video 5, Scaling All Visualization Elements Based on Container Size. In the previous video, we learned about automatically adjusting the size of a chart to the shifting size of its container. In this video, we'll take our scatter plot from last section and make it take its dimensions from its container. We'll then make it resizable and talk through what visual elements you can change on screen size changes. Let's start out with some code that generates a scatter plot, using the same code that we used to generate the scatter plot in the previous section. We'll then place this into boilerplate that we've been using with a div with the ID of class, and begin by establishing a margin similar to the bar chart margin we used in the last video. We'll then need to update a series of lines from our original scatterplot code that had previously relied on static height and width numbers for their values, including the new height and width variables in our x and y scale ranges, such as here on line 92 or here on line 95. We'll also need to update our use of height and width in our transform translate calls, if you'll remember from rendering our x and y axes. In the source code, this is on line 150 and 156, where we previously used static values that adjusted our margins to make them legible and to make sure they fit into the SVG. Now we use our margin values to give our axes a bit of extra room to be seen. Notice how the y-axis uses the left and right margin because it's being positioned horizontally, while the x-axis uses the top and bottom margins because it's being positioned vertically. If you save what we've got and open it in the browser, you should see a site that will take the width of the container as its own, but based on what we covered in this video, won't shift responsively. If you'll continue down the document of sample code, you'll see that we've replicated the same procedure from our last video. We've added a function named resize, to which we've removed the SVG after selecting it, and reestablished the updated dimensions of our container. Also notice at the bottom that we've placed a call to the resize function on an event handler of the window. Pretty simple now that you're getting the hang of it, isn't it? If you save your file and open it in the browser, you should see the same chart, but one that adjusts its size based on the size of the container element. But even though our scatter plot is now more responsive, it's not necessarily usable at a smaller scale. If you'll notice, particularly the y-axis gets incredibly crowded as the window resizes. Let's fix that in our next batch of example code. First, let's fix the y-axis in the initial loading of the page. Then afterwards, we can apply the same fix to the resize function. If you look at the original call to d3.svg.axis that's stored under the variable name y-axis, that's where we should specify the number of suggested ticks. We're going to want a different number, however, based on screen size. So let's use an if-else statement. The width of the container is stored in the variable width, so let's use that. If the width is less than 500, suggest that D3 use 3 ticks. Otherwise, suggest that D3 use 5 ticks for the y-axis. Now let's make the same changes down in our resize function. Save your document to check out how we've altered the tick elements based on our container size in the browser. Essentially, we're just declaring the same value with different attributes, depending on the size of the screen. As expected, when the window size is greater than 500 px in width, there are 5 ticks on the y-axis. And when the screen is smaller than 500 px, there are 3 ticks. It should be noted that this type of procedure can work on every attribute and styling component of D3 visualization, as we'll see in more detail as the course moves along. And if you're looking for an extra challenge before the start of the next section, try and integrate a margin variable into another visualization we've made, checking on the size of the parent container and resizing as the container size changes. See you in the next section, External Data Sources.
Welcome to Section 4 on External Data Sources. This is the first video of the section on integrating CSV data. In the previous section, we covered the basics of responsive design, as well as how to resize visualizations based on their container size, essentially responsibly redrawing visualizations. In this video, we'll set up a local host for external data files and proceed through the d3.csv function to construct a scatter plot. Before we jump into the first topic of the section, setting up a localhost, it should be noted that many viewers may already have a localhost set up, and thus may skip ahead to the next portion of the section. Also, that the following walkthrough of setting up a localhost is centered around setting up a Windows 7 or 8 localhost through IIS, or Internet Information Services. Detailed instructions for setting up localhosts of types other than IIS are available all over the internet and should be consulted if you would like to set up any other type. Alternatively, you can watch through the section before setting up your localhost on your own time. On Windows 7 or 8 machines, you'll want to start by enabling Internet Information Services. Head to your control panel and click on the Program link. Under Programs and Features, you should see the option to turn Windows features on or off. Click there. If it's not already enabled, click the box next to Internet Information Services, the fourth down on my screen. Go ahead and click on it to make sure that all of its subcomponents have been selected as well. You'll need to restart your machine for this change to take effect. Next, let's place our data onto our localhost. Check in the resources for the video and download data.csv. If you've restarted your machine, there should be a new folder under C, titled inetpub. Once you're in C/inetpub, head to www.root. This is where you should place your data.csv file. However, note that if we attempted to load our CSV file from our localhost through JavaScript at this point, we would receive an error specifying an access control allow header error. This involves a header that must be returned from an HTTP GET request from our localhost, or anywhere, enabling external scripts to access the materials on the site. You may need to search for it, but we're going to need to open Internet Information Services Manager to add a universal header that will enable our call to the localhost. If you're on a server configured in another way, Apache, Jetty, so forth, check out the W3 specs on CORS, or enabling cross-domain access to your page, to see what header syntax you should use. For Internet Information Service servers, you'll need to open the Internet Information Service Manager, click on the Sites tab to the left, and then the default Website tab. Click on HTTP response headers, and then add the following header. Access control allow origin is the name, and an asterisk is a value. The asterisk permits scripts loaded on any site to access your site's resources. You may also specify particular sites or IP addresses, like your own, if you want your data to be more secure. With our localhost set up, let's take a look at the data on our data.csv. Upon opening the CSV, we should note that there are a header row in the file. Something to note is as it changes whether you use the d3.csv.parse or the d3.csv.parseRows functions. It's also important to note that there are no spaces in the titles for the header row. If there were, we would need to manipulate the CSV or treat the header row as a normal row and then disregard the data. In short, leading spaces in CSVs disable you from easily accessing the groupings of the object array we'll eventually turn our CSV into. Let's jump into the editor, load the data into D3, and verify the contents. Let's start out with our usual boilerplate. I've gone ahead and added some basic components, including width, height, padding, and a variable titled data. If you open your source code, take a look at line 23, where we've got a D3.text method. Note that we could have used a D3.csv function for our GET request to the localhost, but text is slightly more versatile, allowing you to load CSV, TSV, JSON, and so forth. The only difference is the D3.text method takes a MIME type as the second parameter, which I've specified as text/CSV. The basic format for the D3 text method is the URL source of the data, the MIME type, and then a callback function into which we'll eventually mold our data and build a visualization. Our callback function starts by accepting a parameter called unparsed data, which will accept the results of the D3.text call. In the following line, we assign the value of a D3.csv.parse method to the data variable. D3.csv.parse takes the string that unparsed data currently is and returns it as an array of objects, organized according to their rows, and with the headers that apply to each column of each CSV rows as keys in an object key value pair. Note if our data hadn't had a header row, we would have used the D3.csv.parseRows. We then begin to verify our data with a function called logCountries that takes element, index, and array parameters. Notice we call the function 2 lines below with a forEach method. This uses our previous construction, which tells the forEach method exactly what each we're talking about and accessing the data we want printed. Because our CSV parse function has separated the rows of our CSV into key pair values, one of which was country, we can simply iterate through every index value of the array that is our data variable and look for the country key. We've also console logged a little header. The countries are, new line, all of our countries. If you'll open your code in the browser and check on the console, you should see what you were expecting. The countries are, and all of the countries from our CSV file. Let's head back to the editor and get started on our scatter plot. With our scatter plot, let's check out the relationship between population and GDP caps. You can open up your 4.1.2 HTML source code or edit your own code as we work through it. To start out with, we've created empty array variables for both our GDP caps and population data. We can use the same general for each method on our data variable to push the needed values into these arrays. Utilizing the data in this way will keep us from needing to iterate through our data source in a prolonged manner inside of our scale calls we will eventually use to render the scatter plot. The addition signs make sure that everything that's pushed into our two array variables is an integer, instead of the string format that the CSV is currently held in. Note that besides that, it's the identical format to our previous call to verify the data, and that we call the data for each method on both of our above functions below. Next, we can move to our standard enter and append procedure for scatter plots. Notice that we've passed our data variable on the data method. This will create a circle placeholder for every object in the array. Into the circle attributes variable, we'll pass our GDP cap and population, keys of our data, as the CX and CY attributes that should be iterated through, unlike in our scales, where we're passing the simple arrays we've already extracted the values we need into. We do this as our scales method wouldn't automatically iterate through the objects in our data variable. Besides the few lines of initial data preparation, note the only other difference between a normal scatterplot example is our Windows onLoad function that simply waits so that the chances of our data call having returned are higher before the scatterplot is actually rendered. As expected, we have a scatter plot with 36 points, each corresponding to the GDP cap and population values present in a single object in our array. If you're looking for an additional challenge, you could either add the country values as tooltips to our plots, or give the circles different fill values based on the continent they're from. A hint, adding tooltips can be accomplished by accessing D_country and appending text elements with a class tooltip, while coloring the elements can probably be most easily achieved through placing the continent values into their own array through for each, and then adding an if-else loop to the fill value for the circle. Now that we've established our CSV mastery, let's move on to the next video, titled Utilizing JSON Data. See you then! Welcome to Section 4 of Video 2, Utilizing JSON Data. In the previous video, we covered utilizing CSV files as an external data source for D3 visualizations. In this video, we'll work through the D3.json function, accessing a JSON file that contains color values. We'll then generate random numbers to pair with our color values, and eventually applying the pair to a bar chart. Assuming you have a localhost set up, or set one up last lesson, we'll start by placing our data.json file into the same directory that previously housed our data.csv file. For IIS users in Windows 7 and 8, that should be under inetpub subdirectory www.root. Let's take a look at our JSON data, which isn't quite as nested as many JSON data files are, but allows access to several JSON objects through the colors array key, inside of which we have a number of key pair values, including color name and hex value. After you've placed the file in the proper location to be hosted locally, let's jump into the editor, where we've placed our usual opening variables. Notice that we placed a data variable yet again to afford easy access to the data afforded by our external data source. Below that, we'll want to jump right into the D3.json call. The JSON method takes the URL location of an external data source as well as a callback function. Essentially, it's the D3.text method, save without the middle parameter of MIME type. Notice how our callback function takes a JSON parameter. We'll then use to access our colors array and pass the values onto our data variable that will then console log. If you want to check out the format of the file that we just looked at in our editor in the browser, go ahead and save your document and open it in the browser. Open your console to see what's been logged, as it might be a good opportunity to play around with accessing the data you want from external data sources. Because the main type of data in our JSON file are color values, we want something else to establish the height for the bars in our bar chart. Let's place some new key value pairs into our data object. To do this, we'll need to iterate through our array in the data variable, then push a new key, num, to which we'll assign a random number through the math.random method. We'll do this with the following code on line 29. Using a simple for loop, we'll iterate through our data method, and for each index value, append a key value pair with a key of num and a value of a random number between 1 and 100. Note that math.random comes up with a random number between 0 and 1. That's why we've multiplied this value by 100. The remainder of our code involves a pretty standard appending of recs into our bar chart. Notice we've selected our body, appended an SVG, given it height and width attributes, selected all recs, appended our data and entered, and given the bars of our bar chart's attributes. Notice how our fill attribute iterates through all the values in our data variable, returning the name of colors. Opening our file in the browser should yield the bar chart with the prescribed colors from our JSON data, and with relatively random assigned height values. You can check out the random number function at work by refreshing your page. You should get different heights every time. Having worked through the D3.json method, let's move on to the next video on building a map with GeoJSON, the final video in the 4th section of the course. See you then! Welcome to section 4 of video 3 on making a map with GeoJSON. In the previous video, we covered using JSON as an external data source for D3 visualization. In this video, we'll cover the necessary elements of D3 maps and GeoJSON as an external data source. It should be noted that this video works along particularly well with the second half of Mike Bostock's Let's Make a Map article that can be found at bost.ocks.org/mike/map. This is a particularly clear D3 map tutorial that can be referenced to provide additional information beyond the scope of this video. First things first, included in the course package is a file called unitedkingdom.json. First, you need to place that where you can access it through a local host. If IIS is set up on your machine, the directory is the same as the previous projects, and c initpub/www root. Let's jump into the editor and get started. We've used the usual boilerplate here, except for one difference. We've included a link to the topo.json source code on line 8. Topo.json is an extension of GeoJSON that encodes topology and reduces redundancy in GeoJSON data. Where GeoJSON would plot two paths for shared boundaries between states, Topo.json plots them both as a single path in an arc. This makes including maps noticeably lighter on your page. Topo.json also extends the functionality of GeoJSON with a number of methods, including server-side methods that take GeoJSON data and manipulate it, as well as client-side methods that turn Topo.json data back into GeoJSON for rendering in the browser. Moving into the script, note that we started with our usual variables for establishing the SVG, as well as a variable titled data that will hold our eventual JSON call data in. Proceeding down to the D3.json function, note that it takes a URL location for our JSON, as well as a callback function that will be completed when the GET request returns. Either an error message or the data received will be held in the UK parameter. We'll then console log the data presented to verify it. Let's jump into our browser to check it out. Notice that the data comes back in an object with the type of topology and other key value pairs of arcs, objects, and transforms. The arcs are used to establish the borders of our location data, while the object array holds a number of places and names for labels. Next, let's jump into the elements necessary for rendering the JSON data on the map. First, we'll need to establish an SVG. Then we'll need to access the data we want through the topo.json feature method. The feature method looks at feature collections or geometry collections in geographic data and pulls out the features in a given object. Examples of features include points, lines, polygons, and other simple geometries, often labeled and placed into hierarchical data structures. Feature methods take two parameters. First, the location of your topology data as a whole. This is generally what's returned from the D3.json call. And secondly, the most specific feature that should be returned. In our case, this is subunits, which offer the path data surrounding the regions of the UK. We'll store this in the subunits variable so that we can more easily pass the subunits to the path method as our data to be appended according to the type of projection we choose. Moving down, you'll see both a projection and a path variable. In the projection variable, we've selected a method from the D3.geo object called conic conformal, a mapping projection style. There are 12 common mapping projection styles in D3, and you can check out the documentation if you'd like to learn more about your projection options and what they're good at. For the values that we've passed our projection, Center takes a two-element array, the first value for latitude and the second for longitude. Meanwhile, Parallels takes a two-element array that establishes the northernmost and southernmost latitude values that should be displayed. Rotate takes three values, including longitude, latitude, and roll. If only two values are specified, the roll value is assumed to be 0 degrees. Scale notes how zoomed in the projection should be on its central point. If the scale value becomes larger, the projection zooms towards the center of the projection even more. This value defaults to 150 if not specified, but we'll want to zoom in a bit as to focus on the United Kingdom. We then use the path method to actually render the geographic paths that will create our map. The path method requires the projection data, which we've specified above, a selected SVG, the type element to be appended, in our case path, the location of our data in subunits, and then where the D element, a description of a path on the DOM in an SVG, should actually be taken from. In our case, from the path that we're establishing right now. Both path and projection specifications are required to render D3 maps. Now that we've gotten ours set up, let's see what it looks like in the browser. You should see the United Kingdom featured quite largely on your screen as a result of the 6,000 scale we've supplied. It's a lot of fun seeing the level of detail that can be created with just a few lines of code and JSON data, but we still aren't done. There are a number of other elements in the JSON that we can use to customize the map. Let's start by plotting a few more paths, the data of which is supplied in our JSON. The subunit features provide the outlines for individual nations. So at this stage, we'll point our data method one level further into our hierarchy to retrieve this information. We also provide the attribute of a CSS class titled subunit, to which we'll concatenate the ID of each one of our data points being used in the rendering of these new paths. This is so we could later select these regions through CSS. Jumping up to our styles, we could utilize our recently selected paths, giving each region of the United Kingdom its own color. For Scotland, Northern Ireland, England, and Ireland, as well as Wales, which will remain black. So one final note, let's lower the scale slightly to get a slightly more balanced view of our projection. While there's a good bit more data available in the JSON file, and we could add a number of other features including labels and locations inside of the countries, we're out of time for this section and we need to head on to the next. So let's check out our map. If you're looking for a challenge before the start of the next video, try to append the names of places from our topo.json data. First, you'll start chaining methods to your SVG, selecting all of the class you want to name your text label. You'll then have to provide the data for your labels in the same format the data for the paths was provided earlier in the code. Enter, append text, and provide it with the attributes needed to render it in the proper location. Then pass a text method that returns the names of each. If you can't seem to get the right data out of your topo.json object, remember to console log the object and explore its structure. Now that we've walked through the basics of Geo JSON data, it's time to move on to the next section. Building blocks 4, spicing it up with interactivity, in which we'll work on adding layers of interactivity to some of the projects we've previously worked on. See you then!
Welcome to Section 5, Video 1, in which we'll focus on using transitions to increase interactivity with our visualizations. In the past section, we worked on utilizing external data sources. In this video, we'll start by modularizing our JSON bar chart we made in Section 4.2 so that we can render and re-render our chart depending on what transitions are underway. Then we'll work through some features that D3 affords users in regards to transitions. With our previous bar chart, in which we paired JSON data with random numbers to give our bar's height, let's start by placing the core components into functions that can be called throughout our different transitions. Let's separate the random number generator. The randomizer will take the data value containing our JSON call data and set up a random number pairing whenever it's called. Note that our code inside of the function is identical to our 4.2 code. However, now that it's in a function, we can call it whenever we'd like. Next, let's wrap our code that creates our SVG and bar chart into a function called render. We can go ahead and call these two functions at the bottom of the code, in what will be our initial rendering. If we were to load the code in our browser now, we would see the same output as our previous code, but now that it's modularized, we can call it again in different ways when users interact with our chart. Next, let's jump into our transitions. For the first transition, let's wait for a mouse over event on any of our recs, and then change the fill color, as well as the height and Y values, over the course of 2000 milliseconds, or 2 seconds. Note that we've included this section inside of our JSON callback function that contains our entire script, yet outside of our render function, as we may want to render a new bar chart separately of our transitions. Walking through the previous code, we've used the D3 select all method to wait for a mouse over event on the rect. We then pass an anonymous function in which we use the this selector, or whatever bar the mouse is over, to begin a linear transition over 2 seconds to our new fill, height, and Y values. Note that we've pretty much copy and pasted the values from our height and Y values from the initial rendering of the chart, but we changed ×3 to ×4, providing a might as well be random height value. While transitioning the height in this manner may not be particularly useful for viewing our chart or sharing data, we'll just use it for illustrative purposes to show how to work our way around some of the features of D3 transitions. Now let's chain our .onMouseOut method. The form of this section is pretty similar to the mouse over event, but leaves one question. Now that we've dynamically changed the data of our recs, how do we access our old attribute values to return them to normal and mouse out? The height, Y value, and fill color of our bars have been altered during a mouse over, so we're going to need to insert some new attributes into our original rendering so that we can access the original values in our mouse out transition. Let's head up to the end of the bar attributes section on line 66. In the original render call, here you can see we've added a few new values. We've set each rec's ID to the value of the color name contained in the original data, so that even once the quote fill value of our rect has been changed on a mouse over, we can assign the original fill value again. We've then created two other new attributes for all of our recs, one which stores the original height, and one which stores the original Y value. Returning to our mouse out call, we can assign our original attributes by using an anonymous function that selects the rect that the mouse is leaving, or this D3 select this, and then transitions our fill, height, and Y values back to what they originally were by returning those attributes of the selected rect. Notice this is a difference between the original mouse over section, in which we simply manipulated our original data call, and our mouse out method, in which we've accessed attributes of each individual rect through the select this method. One final event handler will let us reset the chart and utilize our randomizer and render functions. We won't want to chain this to the past two selections because we'll be listening for events on another element. In this case, the SVG. On the double click, we'll select the SVG and remove it. We'll then call our randomizer and render functions again. Let's check out our project in the browser to see if the mouse over, mouse out, and double click events are altering our chart in the way we think it should. Notice that the transition method automatically computes the speed with which elements must be transitioned to fill out the specified duration in ease method. Using linear transitions as an example, the greatest difference between the new and old heights, or new and old colors, the faster the change that must occur relative to the 2000 millisecond duration. With our initial lesson on interactivity completed, let's move on to the next video on some very useful ways in which D3 can help users filter data in visualizations. See you then! Welcome to video 2 of section 5. In this video, we're going to look at a powerful D3 method called filter. It's pretty simple, but enables you to iterate through an array and return a subset of the array if it meets certain criteria. We'll use it to tack some point 2 with a line chart we created back in section 1. So if you open up your 5.2 source code or follow along, you'll see that we have an array of key value pairs with values relating to months and win percentages. We've gone through the basic appending of the SVG and path that uses month data for X values and win percentage for Y values. If we were to truly spruce up the chart, we would want to add scales, axes, and a margin object to keep it responsive. But for the sake of simple illustration, we left those elements out for now. We're going to want to see some visual output for the filtered data, so let's start by selecting all dots on the SVG, entering our dataset as the data attribute, and appending circles. Note that there's a placeholder element for every entry in our dataset, but we'll only want to display some of those losing months. You would want to automate this with a larger dataset, but with ours you can eyeball about what you consider to be a losing value. Let's just say it's below 20. We'll put this into a filter method chained to our previous append. Note that the filter method takes an anonymous function and returns the portions of the dataset that you want filtered out. We can then proceed with styling only those portions of the dataset with a fill value of red. We're also going to want to highlight our quote-unquote winning dots of over 20. So let's proceed to copy the previous circle appending block, while altering filter method to select only win percentages with values above 20. We'll also want to choose another color. I chose yellow. If you save the current code and hop into the browser, you should see what you expected. Our old blue line chart with the uppermost values punctuated by yellow dots and the lowermost values punctuated by red dots. This sort of illustration has its place, but a lot of times you'll want to give users a way to toggle what they're seeing so that they could really explore the visualization. So let's hop back into the editor and create the elements that will toggle our filtered data. You can get fancier and include checkboxes, drop-down menus, and the like, but for the sake of illustration, I'm going to use the two divs with the text winning and losing in them. Now that we have something to trigger an event, we could wrap the blocks of code that append our circles to the SVG in event listeners, and add our circle appends as the callback function. If we were to check out our current work in the browser, you would see the text header in the blue line. Then when you scrolled over the text, the dots would appear, but they still aren't fully toggleable, as they don't go away when you've moved your mouse out of the winning or losing div. Because our previous D3 selections were selecting the divs above our SVGs, we can't apply changes to a D3 select this method. Instead, we'll need a way to select all of our filtered data circles. So let's assign classes to our dots. Notice for our losing circles, we've appended a class called losing dots. And down in our mouse over event for winning, we've included a class of winning dots. We can then use these classes to select each of every one and remove them on a mouse out event. We can chain that to the end of our 2 previous on mouse over events to get our desired functionality. For a final bit of clarity, let's invert the colors of our H2 elements that we're hovering over. I've added 2 classes to our CSS, one titled selected and one unselected, that essentially just invert the colors of our basic div. We can add these sections to the end of the on mouse over and mouse out events. The first adding a class of selected, and the second adding a class of unselected. Note that we've done this both for the winning and the losing event handlers. Let's check out our work in the browser. Note that with your current setup, when you mouse over one of the divs above, it's actually creating placeholder circles for every data point, but just doesn't give those that don't trigger the filter condition any styles. Also note the added clarity of showing which H2 element is being shown. Because we're using the text more as a button than actual text, note that the cursor has remained a pointer, instead of the usual select text cursor. This may be altered in the CSS by changing the cursor attribute to default. Now that we've gone through another exercise on interactivity, it's time to move on to our next video, where we'll expand our repertoire of visualizations a bit. Think of all the crazy combinations you could work through with our current knowledge of interactivity and a few more chart types. See you then! Welcome to video 3 of section 5. In the last video, we covered filtering data with mouse overs in the filtover method. In this video, we're going to be using our exploration of interactivity as an excuse to dive into 2 new D3 layouts and add some interactivity. It should be noted that while layouts are often used to help create the visualization styles for which they're named, at their heart, they're just data manipulation tools that take a certain type of data input and output it in a style that fits to a certain visual layout, whether that's angle values, radius values, placed into standard deviation, and so forth. If you'll open up an empty file in your browser and type D3 layout into the console, you can see all of the layout options built into D3. We're going to work through a few of these in this lesson. Let's jump back into the editor to get started with the pie chart layout. As you can see in the 5.3.1 source code, we started out with the basic variables we'll need, including the height, width, and dataset, and a color variable. Our category 20C scale provides an already selected range of 20 colors that can be applied categorically. We've also included inner and outer radius values. If you want your pie chart to have a donut shape, increase the inner radius value. But for now, we'll keep it at 0. After establishing our SVG, we'll need a variable in which to store our initialization of the pie chart. If you save your work and jump into the browser console, you can check pie layout at work on the data. Type pie parentheses data, and you'll see an array of 7 objects returned, 1 for each data point. If you look into each object, the values of our dataset have been given attributes that are optimized for the presentation of a pie chart, such as a start and an end angle, padding, and their actual value. All these are calculated based on the relationship between the data points and how they'll fit together in the eventual pie chart. Jumping back into the editor, we'll need 3 more blocks of code to render labeled pie chart. First, we'll need to enter our data and attach it to elements. And attach the elements from the objects returned by the data manipulation that the pie layout provides as groups. This will keep our angles, paths, colors, and labeled, all grouped and attached to the same arc element. We'll then translate our pie chart by the outer radius in the x and y values. This is because, as it stands without line 50, our pie chart would render centered at 0, 0, xy values in our SVG, thus only showing up in the top left corner. We've separated out the next block for clarity's sake, but we're basically just giving attributes to the previously appended groups. We'll start by passing the index value of the color variable, which if you recall is the scale of colors by categories. With 7 objects passed into the scale, it should return 7 colors, 1 per wedge. We then specify the data for our newly appended and color paths in our arcs variable. This will tell the path whether or not it should render as a pie or a donut. Finally, let's append our text. We'll chain it to the arcs variable like the previous path appended. The first attribute passes the xy values of the central point in each data point as it relates to our plotted arc. This will center our labels on each wedge. Notice how our transform translate attribute takes an anonymous function that passes each of our data points one at a time into the translate call, defining the centroid of each wedge. We've then specified the text to be added as the value attribute of our data. Enlarge the font size and color it white against the background of the different colors from our color scale. Now for some interactivity. Let's alter our pie chart so that it slowly rotates when we click on it. Besides the simple transform attribute to the arcs, the main device we'll be using here is a set interval call that will trigger a function that rotates a set amount every 10 milliseconds. This is one way you can paste animations. trigger a small animation every 10 milliseconds that the mouse is clicked on an element. Then on mouse up, present a null value to clear the interval, allowing for the animation to start again next time you click. Notice how the interval variable makes use of scope, allowing for itself to be changed inside of the mouse down callback function, yet allowing for itself to remain null on the mouse up call. If you're looking at the rotate call, note that we're providing 3 values. The first is the number of degrees we're wanting to rotate. In our case, this starts at 0 and iterates up by 1 degree every time the rotator function is called, which is every 10 milliseconds. The second and third values are the x and y values that will serve as the reference for the rotation. In our case, 0 and 0 for the top left of the SVG. Let's open up our newly interactive pie chart and check it out in the browser. Well, we could alter the text to spin as well, so as to remain centered and facing upright. It's time to jump into the 5.3.2 source code so we can learn a new layout. You'll see we're moving on to a tree chart. A handy way to visualize hierarchical data, such as data held in JSON files, is often composed of. If you'll look at our catsanddogs.json file that we're going to locally host, it's composed of another number of categories of animals, such as cats and dogs, that are in turn composed of children and breeds. Once our JSON is in the right place, inetpub/www root, we can start off our tree chart with the D3.json call, which will return our data. To properly manipulate data into the form that can be rendered as a tree chart, we'll need to initialize the layout, which takes a size argument inside of square brackets as an XY value. We'll then use the tree layout functionality to process our data. First, we'll create a variable called nodes. Our nodes variable will become an array of objects that have attributes designating what layer of the tree they are in, who their children and parent elements are, their name, and so on. We create this array of objects by using the tree.nodes method. We'll then create the variable links, which will hold the x and y coordinates that will be the start and end points of the lines that will connect our nodes. We obtain this set of objects by using the tree.links method, which expects an array of node objects. Next, we'll actually want to append the nodes. This is all pretty standard as we bind node data into groups, provide the nodes with a class for which they may be selected of node, and position them on our SVG. With a transform translate argument, we pass our nodes data into a function that will take the XY attributes of the objects and establish them as attributes, dx and dy. On the next lines, we could chain to the node variable and append circles, as the nodes are really just our placeholders, or how our data happens to be functioned so that it will become a tree chart. We can continue our chaining and append some text as labels by passing a function that assesses the category attribute of our objects in our data array and appends them as text. If you were to look at your file in the browser, you should currently see a number of tiered blue dots with labels beside them. For the paths between the blue dots, we'll need to harness the attributes in our links variable and append them as a diagonal path. This is similar to appending of our last section with the node data, except for the fact that we're including path-specific attributes, such as fill values, stroke values, and a class of link. If you'll save your file and open up it in the browser, you should now see our finished tree chart. Now that we've seen what the basic tree chart involves, with the appending of both nodes and paths, and the initialization of the d3.tree layout, let's add some interactivity. We'll make the paths change color when they're hovered over, and enlarge the circle and text when they're hovered over. For the paths, we'll select all paths and attach a on mouse over event listener. We'll then use the D3SelectThis selector to change the stroke to red. On our path mouse out method, we'll use a transition and delay our paths from turning back to black by half of a second. This is important because the line is so small that it gives a little leeway to those trying to scroll over the lines and see the connections. For the circles and text, we'll do similar on mouse over and mouse out calls on the circle elements. Remember how earlier we grouped our circle and text into the same node? This allows us to use the this.parent node selector and apply a different font size attribute even though we've actually just selected the circle. Because both the circle and the text share the same parent, this shows how you can traverse to apply a style on a sibling attribute even if it's not what we have selected. Let's check out our finalized tree chart in the browser. If you want a fun challenge, try to figure out how to start with the parent node and only display lower levels of hierarchy on click. Now that we've expanded our skill sum in terms of both layouts and more practice with interactivity, it's time to move on to our new section on mapping with GeoJSON. See you soon! Welcome to section 6, Mapping with GeoJSON. In the previous section we covered transitions. In the first video of this section, we'll look at how to set up a GeoJSON base map. We'll start by finding shapefiles, formatting them, and finally rendering the map. Let's jump right into one of the best locations for getting large shapefile maps. For the US, the Census Bureau's Tiger products offer boundary maps with varying degrees of details, some including rivers, roads, and features. Some of these maps can contain astounding levels of detail and can be quite large. We're going to go with the cartographic boundary shapefiles, and then on the county type map, which you'll notice comes in 3 resolutions. Because we won't be zooming into a great level of detail, let's keep the size of our shapefiles as low as possible and download the 500K resolution. This should show up zipped. Next, we'll want to head over to a site that will help us convert our data, converter.mygeodata.eu. Note that you could either upload simply the CB_2013_US state 50k.shapefile, or you can upload the entire zipped folder. Once it's recognized the contents of your folder, you'll want to specify a number of encoding and formatting components. Note that GeoJSON D3 expects a format called WGS-84 as an output coordinate system. Basically, this means that it expects the coordinates for the objects on the map to be given a latitude and longitude, x and y coordinate. For reading documents, D3 could only read UTF-8 encoding, so we'll need to adjust that as well. For future use, note that you could specify the attributes in your shapefile that you want included in the output. Once you've stored your converted GeoJSON file on your local host, which is in the directory www.root/inetpub on Windows machines using Internet Information Services, let's jump back into the editor. We're not going to use topo.json for this map, but it doesn't hurt to remember that it can be included through the small link on line 8 of our header. This enables some increased functionality, but it isn't needed for the map that we're going to create. First, let's start with some basic width and height components, as well as a variable in which to store our data. Below, notice that we've completed the same D3.json call, into which we passed a function as the second parameter that returns and console logs all of our counties data, as well as attaches it to our data variable. If we were to load this in the browser and look in the console, we would currently see our GeoJSON returned as an object, including a key called features. Inside of features, there are several thousand further objects that contain features such as geometry with given coordinates, as well as properties such as name, A-land, county, FP, state ID, and so on. But though we're not going to look through that entire object in this video, I would encourage viewers to always load their data sources in the console and become familiar with their format, so as to strategize how it can best be utilized for the project at hand. Next, we'll need to append an SVG. We'll also need to append a path. This is a D3geo function that takes our latitude and longitude based GeoJSON data and plots it to a particular projection of the world. The default projection is Albers USA, which is best suited for visualizing US maps, and has a default point size of 4.5 px. For world maps, we would need to specify another projection, such as our previously rendered map of the UK. Because this map is of the US, however, we can just use the normal path generator without feeding in a separate projection call. Next, we'll need to append all of the smaller paths contained in our GeoJSON file. For our current data, this is pretty easy, as we'll just need to pass counties.features as our data for all of our paths, as well as a given fill value. Note that we've also given each of our individual paths a class attribute of counties. This is so we can later select them and apply CSS values more easily. If you save your file and open it in the browser, you should see a pleasantly gray map of the US divided by counties. It's pretty cool the complexity of latitude and longitude points that D3 can interpolate into a map projection and easily handle. You might also have noticed that it takes a second for the map to load with this many paths. Because our map currently doesn't have any functionality, let's jump back into the editor. Because we've assigned our paths a class, we can easily select them and utilize an event listener. Let's use mouse over to turn the counties red when they're hovered over. Remember from previous sections the ever-useful D3.selectThis, which functions the same way as a thisCall would function in jQuery. Also note that we've used our transition property to ease colors back to normal over half of a second once the mouse has left a given county. Now that we've set up our map and given it a hint of interactivity, let's jump back into the browser and see the result. You might notice a slight lag when loading the map. This is due to our using GeoJSON and the large number of paths needed for all of our counties. To fix this, you can instead use topo.json, which lowers the pathing coordinates by combining the boundaries polygons that share borders into single paths. If you open up your console, you can see the object with the type of feature collection, including features of geometry as well as properties. In the next section, we're going to make our current map into a choropleth map, one of the most popular ways to show geographic-specific trends. But don't forget that what we've covered in this section, including the conversion of shapefiles to JSON, the proper encoding and formatting for JSON to be used in D3 maps, as well as how to explore the data structure of your JSON so that you can strategize how to plot future maps. See you in the next video. Welcome to video 2 of section 6, where we'll be learning to make a choropleth map. In the previous video, we set up a basic map of the US with counties. We're going to build off that map in this video by merging more data that will act as choropleth values with our previous JSON and by creating a color scale for our map. Let's get started in the editor with the first component of rendering a choropleth, the data we're going to pass through the color scale. We could go out and grab another JSON file and go through the same process, make a second JSON call, and then merge the two with a for loop, or another loop type. But for our example, let's just generate random values for each of our counties. If you'll remember back a few sections, we can use the math function to create a random number. Math.random in our example create a random number between 0 and 1. So we've multiplied it by 100 to give us slightly larger numbers. We'll put this call to the math.random function inside of a for loop that will iterate through our data, adding a choropleth value for each county to our list of properties, such as A-land, county FP, state ID, and so on. Notice we've wrapped all of this in a function called randomizer so that we can make sure to call it after our JSON data is already assembled. Now we'll want to set up our color scale. D3 interpolates color values as the range of a domain in a number of ways. It can compute a quantile color scale, which groups values into a few quantiles. It can generate categorical scales, or linear scales that slide between different shades. For our map, let's use a linear scale. Notice I've inputted 3 RGB values. These are from a very helpful site called colorbrewer2.org by Cynthia Brewer. A good bit of science goes into making these themes, and after you choose a color set you like, there's an export button that lets you copy and paste directly into the JS. The color scale I chose ranges from off-white to bluish-green, but feel free to choose whatever scale you'd like. Notice that we've placed the scale in a variable so that we can then call it and pass in our choropleth values. The values computed in our color scale will be between 1 and 100 and will be outputted from off-white to bluish-green. Now that we have our color scale set up and a new data set that we can attach to the data for our counties, let's jump into styling the paths that are already on our map. Here we'll delete our attribute fill method from our previous source code and replace it with the .style method. .style takes care of changing the given value back to a string so that it can be applied after it's computed. A nice step to have taken care of, particularly for larger data sets. Into our .style attribute, we'll pass a function for the value, in which every data set that has a choropleth value returns the color value that's the result of passing our choropleth value through our color scale. If there's no choropleth value, we return the color gray. Well, our data is random, so it's a bit of a moot point regarding what the map is quote-unquote showing. It's a good habit to make sure you're using categorically distinct values that represent an actual spectrum. For example, if we've chosen a bluish color just short of black, then counties that truly have no choropleth values might look as if they're just one end of the spectrum of our values, instead of categorically distinct. Now that we've applied our color scale as a style to our previous map, let's check it out in the browser. As with the last video, the size of our GeoJSON file may take a moment to load. It should be at most 15 to 20 seconds. And again, if you were to implement a map of this level of detail on a live site, you would want to consider either topo.json or a we're working filler image while it loads. You'll notice that our color scale has been applied to our choropleth values and outputted a variety of hues ranging from white to darker blue. Now that we've worked through one choropleth map, including merging data and a color scale, you can do the same with your own data. Let's head to our next video, in which we'll add tooltips and a legend to our map, really rounding out the visualization. See you then! Welcome to video 3 of section 6, in which we'll add tooltips and a legend to our map. In the previous video, we created the choropleth map that we'll be using in this example. Let's jump right into our code on line 123, where we begin by setting up our legend. First, we'll want variables for the pixel size of our rect as well as the spacing. Further into the course, we'll make all of this responsive, but first we have to make it the good old-fashioned way. For the legend to be in the center, we'll also want a value that establishes the middle of the SVG, called margin maker. We can then jump into creating the legend with our usual .data/inner progression. Notice that we've appended a group element. This will allow us to position the text that will go with our legend squares relative to the squares themselves. Through the horizontal variable, we obtain our xTranslate value, the first clause of which makes room for the new legend squares by multiplying by the index, and the second by centering the squares with the margin maker and spacing. This is so that the two squares in our legend won't be stacked on top of one another. Also notice that in our data method, we've inputted our color.domain as our value. This returns the highest and lowest input numbers to color, in our case 1 and 100 from our random choropleth value generator. Next, we'll actually want to generate our squares by appending recs. This section is pretty self-explanatory. taking the 18px value from our legend rect size variable and applying it as the height and the width, as well as taking the color value from our color scale passed through as our legend data. Let's continue to add some text. If you look at the source files, we've included a font size in our CSS, and could do more styling if we chose. We'll want to append text to our legend variable, which will also add the text to our G elements. We'll then give it an X and Y value relative to the containers in which the recs are in as well. We'll then simply return the value given in the legend data call, 1 and 100, as our text. If you save your file and open it up in the browser, you can see two legend recs and their labels. Many legends involve more values, and rendering values from your color scale as your data for a legend element is just a matter of what type of color scale you first created, and how you call it in the data method. We'll move back into the editor and add our tooltips. We're going to use the same basic method we used back in section 2 with our bar chart. First, we'll add some basic styling to the div that will contain our tooltip. We'll then we've given the div a dark blue background, 100 pixel width, 28 pixel height, and positioned it absolutely so that it will hover over the map at where your cursor is for mouse events. At the bottom of the code, we have appended our div, making them invisible for a time with an opacity of 0 and providing them with a class of tooltip. We'll want to actually change the way they render in mouse on and mouse out methods, which will chain to our original appending of our paths. We'll add them in at this point because you have to use event handlers on a selection, and this is the point where we have our paths selected. Then you can also modularize the code and use a D3 select method to chain the on methods too. Notice what's going on in the mouse over event. First, we're ramping up our div opacity to 0.9 over 1/5 of a second, and then we're inserting some HTML into our div elements, namely choropleth value in bold, to which we've appended our d.properties.choropleth value. We're then placing the div at the point of the mouse, adjusted just slightly to the top by subtracting 28 pixels from our D3 event page Y value. Remember that the D3 event page method returns the pixel value of the XY location of our mouse when the given event was triggered. Our mouse out event is a little simpler, simply reducing the opacity back down to 0 over 1/2 of a second. If you save your file and check it out in the browser, you should see what you expected. Perhaps you have different style requirements for your map. But we've worked through the basics and have a map that we can continue to build on in the next section, where we'll make our current map responsive. See you in the next video. Welcome to section 7, titled Making It Mobile First. In the last section, we looked at making D3 maps with GeoJSON. In this section, and particularly in this video, we'll make our map more responsive, rendering it at different dimensions depending on screen size, as well as adding in a loading GIF so that users know to wait for the map to load. Let's jump right into our editor. The 7.1 source code file starts off where we left our choropleth map from the last section. We'll want to delete the static height and width variables at the start and replace them with a margin variable, as we did in our earlier section on responsive design. We'll declare a number of variables in a row using the parseInt function and a D3 selection to get the width style value of the body element on our DOM. After subtracting the width of our body by our margins left and right, and computing our height in relation to our width, we have a way to dynamically grab dimensions for our visualization as the body size on our screen changes. Well, what we've typed already can be used to resize the map container, or SVG based on our screen size. We'll need to access the scale method of how the paths are projected to adjust the actual size of the rendered map. Remember that D3 maps render according to the Albers USA projection if not specified. So let's simply store that method in the projection variable and chain in our scale method, of which we've taken a width, which should adjust automatically with our margin variable, as well as translated the width and height so that our map should be centered within our SVG. Finally, we use the D3.geo.path method and feed it the projection to ready the normal rendering process, while including our responsive height and width as margin values. If you were to load our code now, it would automatically adjust depending on the size of the body element, which adjusts according to the window size of our browser. But we'll want to set up an event listener on the window and call a function called resize whenever this listener is triggered. If you'll head over to 7.1.2 source code, we can begin this process. As in past exercises, we've selected the window, and on our resize event, have passed our resize function. Notice that our resize function begins by establishing the new width and height with another parseInt method. We'll reapply these new values to the projection, and we'll adjust the actual map div that holds the SVG with the same width and height variables. The only thing left is to re-render the actual paths that create our map, which we do in the final lines of the function, through providing our path values as the new D attribute of everything with the class of county, which, if you'll remember, is every subunit of paths in the entire map. If you want to save your work and check it out in the browser, you should see a map that fits onto the initial screen size when it's loaded, but also responds when browser size is changed. Due to the complexity of the GeoJSON, loading is still a bit slow. So let's jump into an easy way of including a GIF to show the user that we're loading. A plugin called Spin.js is shared under an MIT license, isn't CSS, image, or resolution dependent, and renders nice loading GIFs. Check it out on the following link, or in GitHub, where there's a short rundown of its functionality. If you're working along, feel free to download the minified version and save it on your local host, so that you can access it as a resource to your code. Once you've done this, you can create a variable that stores all of the options related to the loading GIF, such as lines, length, width, radius, speed, direction, and so on. As our spinner will be running early in our code, notice that we've placed our ops or options variable towards the top. Only a few components are needed to trigger the spinner, including a target location, which is specified by document getElementById spinner, a new spinner call that takes your options variable, and a spin method that's past the target of where you want the spinner to appear. This will start the spinner when the code runs through this point, which is before the JSON call. And by passing a false value to the spin method, you could stop the spinner whenever you want, like we've done towards the top of the JSON call, spinner.spin.false. Now our map informs the user that their map is loading, loads the map, and map container size to the window, and changes the size of the visualization if the browser changes. It's still a little slow, but this is something you could fix by using a smaller dataset, or turning your dataset into topo.json. Now that we've added some greater functionality, let's check out our current map in the browser. Now our map informs the user that the map is loading, loads the map and container size to the window, and changes the size of the visualization if the browser size changes. It's still a little slow, but this is something you could fix by using a smaller dataset, or turning your dataset into topo.json. One final tool you might want to check out if you're merging large datasets for a visualization, which can take a long time, is Mike Bostic's Q.js, which is available at the following link. This enables you to queue up the order in which you feel like your external datasets should load, as well as what functions should await these loads. This saves the additional wait time of having functions fire before the dataset is loaded. Next, we'll look at how our visualizations can fit into a larger responsive framework with Bootstrap. See you then! Welcome to video 2 of section 7 on integrating Bootstrap to our visualization pages. In the previous video, we looked at drawing maps at different screen sizes. Now let's look at altering the flow of the DOM as screen sizes change through a super responsive framework called Bootstrap. If you remember back to section 2 where we dealt with breakpoints by applying a flexible grid that would then shift at larger breakpoints, well, that's what Bootstrap brings to the table, but with a lot more features. You can check out what the library offers at getbootstrap.com, and you'll want to at least copy the CDN that's on line 8 of our current document. You can also choose the features you would like to have in your Bootstrap compilation and download custom versions from the site. Besides a number of other features, Bootstrap offers a 12-column system that adjusts to 4 screen sizes, including extra small, small, medium, and large. With simple predefined classes, the framework is mobile first, with built-in media queries for small, medium, and large size screen. Let's check out how it works. After you've added in the CDN, let's create 4 divs with the class of row, as we've done in row 19. And inside of those, put 12 one-column divs, an 8 and a 4-column grid, 3 4-column grids, and 2 6-column grids. Note that Bootstrap rows always contain 12 columns, no matter the screen size. Notice that each is designated MD for medium. Because Bootstrap is mobile first, the styles attached to these classes will be applied to medium-sized screens and above, at least until we give divs their classes for large-sized screens. Finally, let's add some borders to the divs so we can see what's going on. If you'll save your document and open it up in the browser, you should see something similar to our screen here. If you adjust the window size, everything designated a medium screen and larger will display in 4 rows of columns. The first with 12 individual columns, the second with 8 and 4, the next with 3 4-width columns, and then 2 6-width columns. Its screen size is smaller than medium. Notice how everything stacks vertically. That's because styles are applied to things larger or equal to medium screen sizes through D3's built-in breakpoint. It's simple to dictate different grid value classes for different screen sizes. If you'll jump back into the 7.2.1 source code, you should see that it's simple to dictate different grid value classes for different screen sizes. You simply place them with a space separation in the class declarations of our previous tag, so you could end up with the same div that takes up 1 of 12 spaces on a medium-sized screen, 2 of 12 on a small, and 3 of 12 on an extra small screen, essentially allowing all 12 of these divs to fit on the same row for a medium size or above screen, allowing only 6 to fit on the same row for a small size screen, and only 4 for an extra small screen, and bumping the remaining divs into their own rows. If you're in need of additional explanation, it's always good to check out the actual documentation for Bootstrap, which has a number of helpful examples for beginners. Get bootstrap.com/CSS. If you'll jump into the 7.2.2 source code, or just follow along, you'll see I've divided our Bootstrap page into a series of sections. Top into a header menu, the second row into a content area, the third into a thank you sponsors section, and in the final row into a footer element. We've inserted some filler text, and we've also given some colors. If you check out this version of the document in the browser, you should see a simple mock-up of a page that's responsive in a similar way to our 7.2.1 code. Now that we have a basic layout with which to play around with, let's add in a visualization and make it respond within our responsive framework. Because the size of our Bootstrap divs will change as the window resizes, and our chart div is inside of one of those divs, we'll want to define our width through selecting the chart div and obtaining its width element, as we've done on line 84. We can chain this with our margin and height variables, as we've been doing in the past few examples. Next, we'll need to go through our typical data binding and appending of shapes procedure. We've done this many times for recs at this point in the course, and remember they require fill, height, width, x, and y values to render normally. If we were to load our code in the browser with just the D3 code we've already walked through, our bar chart would size itself to whatever screen size the site was loaded at, but you would have to refresh the page for it to update to changing page sizes. So let's throw in an event handler for window resizes, as well as a resize function. Notice that our resize function begins by removing our previous SVG on line 121, and then appends a new chart with an updated height and width variable based on the current width of our chart div. It's good to note that with the ability to circumvent breakpoints with Bootstrap, it's a great jumping off point if you're going to be positioning multiple visualization elements side by side, like on a dashboard. Let's check out the final result in the browser. The size of our bar chart resizes as the size of its container div is changed. With our Bootstrap layout and visualization concluded, let's move on to the next video on the very helpful responsive visualization tool, Pym. See you then. Welcome to video 3 of section 7 on integrating Pym.js into your page so that it's easier to manage your visualizations. In the last video, we looked at integrating visualizations into Bootstrap, the knowledge of which paired with Pym should enable you with some practice to integrate visualizations into the flow of projects that are larger than simply a single visualization. Pym isn't good for every project, but here's what it does. It renders iframes, which could be used to bring content cross-domain and bypass conflicting CSS or JS on the rendering page. Because iframes can be somewhat hard to make responsive for both width and height, meaning it could be tricky to keep the aspect ratio the same, Pym adds regularity to the process, keeping width and height responsive within the container div. It makes your page's code a lot neater and cleaner, and avoids conflicts in the event that you want to share a number of visualizations in the same space. First, we'll need to download Pym.js. You can find it at the following site in downloading the compressed version. It may show up as text in your browser, in which case just save it as a .js file and add it to your preferred location in your code base. Because an iframe renders a page from another location inside of a div, we'll need to include Pym.js in both on our parent page, the page onto which we want the visualization to be rendered, and our child page, the page that is to be rendered inside of our iframe. So let's include the following CDN in both. Our Pym is going to be taking cues from Bootstrap regarding when to resize the iframe. In the parent file, you'll want a specified div where our iframe will be placed. I'll give it the ID of container. And then the file can be made the parent page for our Pym purposes with one simple line of code. The format, saved in a variable on line 30, is new.pym.parent. Pass 2 parameters, the first of which is the location we want our iframe appended, and the second of which is the location of the child code. Additional callback functions may be passed in the brackets at the end. Into the child page, we'll pass a similarly simple declaration that we placed at the bottom, new.pym.child. If you wanted to pass a resize function or additional options, they would be placed in the brackets inside of the parentheses after the child. To see the full documentation of the number of built-in methods, Pym.child method, check out Pym.js's GitHub. Next, we need the visualization that we're going to place inside of the iframe. If you check out the 7.3 child sample code, you might recognize the code that we've worked on before. I've pasted in a labeled scatter plot from one of our previous sections. You can try out the Pym with any visualization you like. Now have a visualization at a tangle-free and easy to manipulate frame. I've included a media query in the parent document. It changes the container size when the window size is less than 500 px. If you open up your parent file in the browser, you should see exactly what you would see in the child file. Only if you check out your DevTools or console, you should see the chart is encased on an iframe. Plus, our entire document consists of about 10 lines that were boilerplate. Scale your window down and see how easy it was to alter the iframe when our screen is below 500 px. Yes, our particular sizing change to the iframe is a bit crude, but illustrates an easy way to make your visualizations responsive while keeping your site files free of clutter. Simply make the iframe itself responsive and contain your D3 in a separate file. Now that we've covered the basics of Pym, it's time to move on to our last section, where you continue with your studies, useful libraries, and other resources to help you continue your study of D3 in the future. See you then. Welcome to Section 8, in which we'll recap what we've already covered, as well as look at resources that can help you progress in your data visualization skills, or simply answer questions you might have about some of the projects we've worked through. In the previous section, we worked on making our visualizations mobile first, with media queries, Bootstrap, and Pym. Recapping what the course has covered so far, we've learned about a number of charts: bar, line, scatterplot, pie, and tree. We've also learned the basics of D3. We've covered interactivity and how to make choropleth maps. And finally, we've tied our visualizations together by covering responsive design. It's as good a time as ever, towards the end of the course, to go over some other resources that can help you in your journey to mastering D3. First off is the D3 documentation. It should be your first and last resource when it comes to nailing the specifics, syntax, and functionality. If you're looking for ideas on how to represent your data, there are a number of good galleries of D3 visualizations which could lead you to the proper visualization format, often with source code, and also often use some pretty awesome tricks for concise and beautiful code. Next comes the D3 layouts documentation, which provides for a number of built-in visualization types like force-directed graphs, hierarchy layouts, bundle construction, and layouts like those we worked through, such as pie and tree charts. The next section includes links to all of the libraries and plugins we used. Most of them are extremely powerful, so if you want to do something related to mapping or responsive design in D3, you should definitely check out their documentation. Finally, a few more libraries and features you might find interesting. The first is a link to a quick run-through of HTML5's geolocation API features. These can be integrated with D3 maps to tailor the mapping experience to the user's location. Next is Geo.js, a library by Mike Bostic that helps you fine-tune when asynchronous calls and the related callback functions run either through Node.js or in the browser. It can help parts of your page from running before the necessary data is gathered. The third link in this section is a user-contributed list of D3 plugins that cover a variety of applications. If you think you've missed something in the past videos, or if you want some materials to really step you through chart types that weren't covered in this course's video, check out other free and high-quality tutorials. Now that we've laid out a few continued resources, let's head over to the next and final video on who you should be reading and following. See you there. Welcome to video 2 of section 8, titled Who to Follow, What to Read. In the previous video, we recapped the material we've covered in this course and looked at some additional D3 specific resources with which to improve your skills. In this video, we're going to look at the broader field of data visualization, emerging web standards, and some of the biggest names in the field. Let's start out by looking at web standards in general. It should be noted that D3 is completely in sync with current web standards, allowing for interaction directly between the HTML, CSS, SVG, and JS elements on the page. This helps with debugging, keeping current for browsers, and allowing you to become a better D3 developer by simply learning more about basic web standards. Documentation can get a little bit overwhelming unless you know where to look for it, but everything else on the list is a great read. As far as people or teams you should follow, Mike Bostic, one of the creators of D3 and graphics editor at the New York Times, is a great source to follow, as well as Ian Johnson and Jerome Cuquier. The NPR Visuals team develops a number of tools to help other data visualization makers, and often comments on how and why they made their own visualizations. From here, I'm going to leave you on your own. I hope you've learned a great deal in this course and that you can continue to use sections of course code and video as reference materials. Have fun coding D3!